Hi everyone, this is question 4 of NZQA Scholarship Physics for 2022. This question is called Orbital Dynamics, so let's get straight into it. The James Webb Space Telescope, JWST, has a mass of 6.16 times 10 to the 3 kilos. It was launched on Christmas Day 2021 and is now orbiting at a point called the L2 Lagrange point, where it will remain in a direct line with the Sun and Earth as shown on the right. State the period of the orbit of the JWST around the Sun. So this is a state question and they give you one line of working. So it basically tells you it's a very straightforward deduction that you have to make. But basically, if the Earth rotates around the Sun, then the JWST rotates around the Sun at the same time. So basically, whatever the period of the Earth is the same as the period of the JWST. And we know the period of the Earth is a year because that's the definition of... Oh, sorry, not the definition. That's just how long 1 year is how long it takes for the Earth to orbit around. But they tell us it's 365.25 days. So t is equal to 365.25 days. Okay, and then part 2 says calculate the net force acting on the JWST at the L2 point. So to do this, we can just look at the gravitational forces. So the Sun is exerting a gravitational force. Oh, sorry. What is going on? The Sun is exerting a gravitational force, and so is the Earth. So we can consider them individually, but basically the total force that he'd experience, or the JWST would experience, is the sum of these two. So it would be Fg equals F Sun plus F Earth. So we have Gm, and let's call that S for Sun, M, divided by R and then Sun squared, plus, and then Gm and then Earth, and then M and then R Earth squared. And then we can factorize out G and M, just because makes the calculation easier, makes the substitution easier. RS squared plus ME RE squared. And then you can substitute our values. So G is 6.67 times 10 to the negative 11. M is the mass of the James Webb Telescope, so 6.16 times 10 to the 3, or the lowercase m. The capital MS is the mass of the Sun, 1.99 times 10 to the 30, and the capital case M, E, is 5.98 times 10 to the 24. Radius of RS, well, that's just the different distance between the Sun and the James Webb Telescope. So that's this distance combined with that distance. So in total, it's 1.5 times 10 to the 11 plus 1.5 times 10 to the 9. And then RE is just this distance here, 1.5 times 10 to the 9. So once you make all those substitutions, you will get a value of 36.7 newtons. So now we move on to part B of question 4. An approximation for two bodies in orbit around each other is that the period t of the orbit can be determined using the relationship t squared equals n and so on, where r is the distance between the center of mass of the two bodies and m1 is the mass of the more massive body. Now in your studies of physics to do with orbits, this should be familiar to you as it should be one of Kepler's laws that you derive. Okay, but moving on to part B, one assumption of the relationship above is that M1 is much greater than M2. So M1 is this thing in the middle, M2 is this thing on the outside. And then part 1 says, explain why it is necessary to assume that M1 is greater than M2 to derive this relationship, or much greater than M2. Okay, so if we consider the fact, let's say that M1 was not greater than M2, or much greater, and so they have like comparable masses, well then the center of mass would probably be somewhere around here. That means instead of M2 orbiting around M1, it's instead orbiting around the center of mass. And that doesn't make sense anymore because this R and this R are different. And this R is used for the centripetal force and this R would be used for the gravitational force, which would not be quite right when we equate these two to derive this relationship. And so basically, if we instead make the assumption that M1 is much greater than M2, then the center of mass of the system will be somewhere, I want to put that inside M1, but it's hard to draw. But let's imagine the center of the mass of the system to basically be inside M1. And that basically means that M2 is now fully orbiting around M1 because that's where the center of mass is. And also, this distance R is equal to R. So the radius we use in the centripetal force formula is equal to the radius we use in the gravitational formula. And so basically, the main thing that we're trying to say here is that center of mass would be inside M1, so that the R used in, so we have the centrifugal force and the gravitational force are equal. And this is quite fundamental because Fc equals Fg is the starting point for this derivation up here. And so if the R's weren't equal in either of the two sides, then you would have some issues as to actually getting to this stage. And so part 2 of this question asks, state another key assumption of this relationship. Well, another key assumption is that the orbit is circular. This is something you just sort of have to know. Usually in actual planetary orbits around like the sun or something, it's an ellipse where the sun is at one of the foci of the ellipse, but that is not content that you would be expected to know for scholarship. But you should know that the orbit is circular. So now we move on to part C of question 4. In the case that M1 is not much larger than M2, show that the period of the orbit is given by the relationship t squared equals whatever. Any other assumptions made for the relationship given on page 12 are still valid. So the one other assumption we made was that the orbit was circular, so we can keep making that assumption. But now, because M1 is not much larger than M2, we sort of have to refer back to what we were talking about before. And so what basically happens is if you have M1 over here and you have M2 over here, their center of mass is probably somewhere around here. And we can call this distance x center of mass because it's the distance between M2 and the center of mass. And it's also the distance that you'd be using for centripetal force. So if we have centripetal force, it'd be mv squared. Actually, it'd be m2v squared. The centripetal force acting on M2 would be m2v squared divided by xcom. Now it's using this radius because this M2 would be orbiting around specifically the center of mass. And so that is the centripetal force acting towards the center of mass. And so the radius is the distance between M2 and the center of mass. But if we have instead as well Fg, because the centripetal force must be produced by the gravitational force, G and then M1, M2, all divided by R squared. And this distance here is R. Now this distance here is still R because we are considering the gravitational force between M1 and M2. And it's still their entire separation which is relevant to this equation because it's the distance between the two masses. Okay, great. We have this expression, we have this equation, but nowhere in this do we see the term xcom. So we kind of have to deduce what xcom is. There's a formula for xcom. So xcom is equal to, so let's say we are measuring from the point M2. That means we have M1 and then x1 plus M2 x2 divided by M1 plus M2. This is just the formula for center of mass. M1 is just M1. M1 is just M1. And x1 is R because M1 is at a distance R from M2. And we are measuring from M2. And then M2 and then x2 would be 0 because measuring from M2, the distance from M2 to M2 is obviously just 0. So 0. And then divided by M1 plus M2. So in overall, we get M1R divided by M1 plus M2. So now we can continue with our derivation using the this centripetal force equating with the Fg. So we get M2v squared xcom equals gm1 m2 divided by r squared. We're running out of space, so I'm just going to put it down here. So m2v squared xcom equals gm1 m2 divided by r squared. Okay, so v is equal to, because the M2 is orbiting around the center of mass, v is equal to the rate at which it orbits, and so it's equal to the circumference, so 2 pi xcom, divided by the period, because it takes a whole capital T, a whole period to orbit around that circumference, and that is also equal to its velocity. So we get m2, and then we get 2 pi xcom divided by t all squared, and then x com, or not squared, sorry. And then g m1 m2 divided by r squared. Okay, now we just have to simplify. So m2 times 4 pi squared x com squared divided by t squared divided by x com. These two cancel, eliminating that square on top. So we get g m1 m2 on r squared on the right hand side too. Okay, so what happens if that cancels? We have m2 times 4 pi squared times x com divided by t squared equals g m1 m2 divided by r squared. Okay, they've asked us to find this equation where t squared is the subject, so we have to make t squared the subject. So we can flip both sides of the equation to get m2 times 4 pi squared x com equal to g, oh, actually the other side would be flipped as well, so it'd be r squared divided by g m1 m2. Okay, and now we find that the m2 is also cancelled. Great. So then t squared is equal to, and then we would get 4 pi squared r, so I'm just multiplying, and x com divided by g m1. And now finally we can use that expression we found for x com, which is this. So x com is equal to m1r divided by m1 plus m2. So then we find that this is equal to 4 pi squared r times m1r divided by m1 plus m2, or divided by gm1. Okay, so this is equal to, oh, there is, did I miss this? Oh yeah, I missed this square here. Okay, so 4 pi squared, and then this be r cubed now, and then m1. And then we put the m1 and the plus m2 at the bottom because it's being divided. So m1 plus m2. And don't forget the gm1 at the bottom. And we find that these two m1s cancel. So we just get 4 pi squared r cubed gm1 plus m2. And if we check up here, it is the exact same equation. And so we have successfully derived it. So now we move on to the final part of question 4, part D. The phases of the moon are caused by the relative positions of the sun, earth, and moon. A full moon occurs when the sun, earth, and moon are directly aligned. The moon takes 27.3 days to complete one 360-degree orbit around the earth. However, because the moon must orbit more than 360 degrees to return to a direct alignment with the earth and the sun, as shown in the diagram on the right, the time between one full moon and the next is more than 27.3 days. Show that the time between one full moon and the next is 29.5 days. Okay, so what they're trying to say is, as the earth orbits from here to here, instead of, if the moon had traveled exactly 360 degrees, it would still be somewhere around here. But the thing is, it needs to travel a bit more than that in order to catch back up with the earth so that it's aligned again. So it's traveled a bit more than 360 degrees. So it could be like 400 degrees or something. But for the sake of this question, it doesn't actually matter how much further it travels. Okay, so what we're trying to say here is, okay, the additional angle, the angle rotated by the earth, let's call it theta e. And so the angle rotated by the full moon is therefore, we call that theta m. So I don't know where to draw it, but let's say it rotates, it would rotate from here all the way until, it would rotate from here all the way to here and then back again. So it'd be, let's call that theta m, hard to see, but that's just the full rotation of the moon. That is basically it'd be 2 pi radians, so it'd be the full orbit plus another theta e to catch back up with the earth, basically. So then how do we work with this? Well, we're trying to find the time, right? 29.5 days. So we're trying to convert theta into something to do with time, and so we can use omega. So we can say omega m, or the orbital velocity or orbital angular velocity of the moon, times the time. Times the time. Equals 2 pi plus, and then same idea. It'd be orbital velocity or orbital angular velocity of the Earth times t. Okay, so we're trying to solve for what t is because because that is what the question is asking for. So t, and then we do a bit of rearrangement, and you'd end up with something like this, equals to pi. And well, we can figure out what Wm and We are because we know the period of the orbits. So we can just substitute W for 2 pi over t, which is a formula. And we have period of the moon, period of the earth, and their orbits. And we'll notice that these 2 pi actually cancel out. And so we get t 1 over tm minus 1 over te is equal to 1. So t is equal to 1 divided by tm minus te. Right? We know tm is the time it takes for the moon to orbit just once, so 27.3. And then te is the time it takes for the Earth to orbit the Sun just once, and that is 365.25. And so if we put this into our calculator, 1 divided by 27.3 minus 1 divided by 365.25. We get 29.5 days, as they expected us to.